When you take an antibiotic, you're not just swallowing some medicine. Nope, you're actually deploying a super specialized weapon system. So I thought, let's open up the playbook, right? Let's see exactly how these microscopic agents wage war on the infections inside all of us.
So, what is their secret? I mean, how do they target and take out bacterial invaders with such incredible precision? Well, that's the big question we're going to tackle today. We're going to break down their military grade strategies.
All right, first things first. To win any war, you gotta know your enemy, right? And in this case, the enemy is the bacterial cell. So let's get a closer look at our target. Okay, so I want you to picture a single bacterium as this tiny, self-sufficient fortress. Seriously, it's got this tough outer wall for protection, and packed inside it has all the factories and blueprints it needs to run itself and, build more fortresses. This whole thing, that is the target. So antibiotics don't just have one trick up their sleeve. Nope, they have a whole playbook with 4 main strategies for breaking into this fortress and winning the war. Let's break them down, one by one. So what's the most direct approach? Well, you go right for the defenses. Strategy number 1 is a full frontal assault on the bacterium's main line of defense, its cell wall. Now, this demolition crew is led by a really famous family of antibiotics called beta-lactams. You've definitely heard of them. This includes weapons like penicillins. So, here's how they work. They basically stop the bacterium from building or repairing its walls. And without those repairs, the whole structure just gets weaker and weaker until, pop, it bursts. It's a super effective strategy, but, and this is a big but, it has a major weakness. It only works on bacteria that actually have walls. So an enemy like Mycoplasma, which doesn't have a cell wall at all, is totally immune to this kind of attack. Okay, so if you can't just knock down the walls from the outside, what's plan B? Well, you sneak inside and cause some chaos. Strategy number 2 is all about industrial sabotage, basically shutting down the protein factories. See, bacteria have these little protein factories called ribosomes that they absolutely need to function. You can think of a ribosome as a 2-part machine. Now, some antibiotics, like the tetracyclines, they go in and jam up one part of that machine. And others, like macrolides, they target the other part. Either way, by messing with the assembly line, these antibiotics just shut down all production. The cell can't make the proteins it needs, and it basically starves. But hey, why bother just shutting down the factories when you can go right for the source and corrupt the blueprints themselves? And that, my friends, brings us to strategy number 3, a direct assault on the bacterium's core programming. We're talking its DNA and RNA. Yeah, this is basically an assault on the command center. And different weapons have different targets. You've got fluoroquinolones, which jam up the enzymes that are trying to copy the DNA. Then there's rifampin, which just stops the instructions from ever being sent out. And then you have metronidazole, which is, wow, it's even more brutal. It literally creates toxins that shred the DNA to pieces. Without its core instructions, the bacterium is just done. All right, our last major strategy is less of a direct attack and more like a siege. The idea is simple. You surround the fortress and cut off its essential supply lines until it just starves. So it turns out bacteria need this nutrient called folic acid to build new DNA and multiply. Now, we humans, we get it from our food, but bacteria, they have to make it from scratch, and that's their weakness. Drugs like sulfonamides and trimethoprim are designed to block that production line. And what's really cool is they often work as a team. They're used together to create this 1-2 punch that completely shuts down that vital supply line. Pretty clever, huh? So we've got these 4 powerful strategies, right? But depending on the specific weapon you use, the end goal can actually be a little different. Is the goal a swift, clean kill, or is it more about just neutralizing the threat? This brings us to the 2 main outcomes of the battle, killer or inhibitor. Okay, on one side you have the bactericidal antibiotics. Think of these as the assassins. Their job is to kill the bacteria straight up. Then, on the other side, you have the bacteriostatic ones. Now, these don't kill directly. Instead, they just stop the bacteria from growing or multiplying. They essentially hold the enemy in place, which gives your own body's immune system the time it needs to come in and clean up the mess. So yeah, 2 totally different paths to the same victory. Okay, now that we get the strategies, let's take a quick peek into the armory. All of these different weapons can be organized into distinct chemical families, kind of like a catalog. This table gives us a nice little glance inside that armory. You can see families like the penicillins and cephalosporins. That's part of the wall-destroying crew we talked about earlier. And then you've got macrolides and tetracyclines, our protein factory saboteurs. See, each of these families has a different chemical structure, which means it's a different type of weapon, designed for a very specific kind of fight. A doctor's job is basically to be the general, choosing the right weapon for the right battle. So, with this incredible arsenal and all these sophisticated strategies, you'd think we've pretty much won the war against bacteria, right? Well, that's not exactly the whole story. The battle is, in fact, far from over. Because here's the thing, the enemy is fighting back. Bacteria are living organisms, and like any living thing, they evolve to survive. They're developing their own counter strategies, like building thicker walls or creating these tiny pumps to just spit our drugs back out, or even making enzymes to neutralize our weapons. We call this antibiotic resistance, and honestly, it is one of the single biggest challenges facing modern medicine today. Our amazing battle plan has saved, literally countless lives. But the enemy is adapting, and they're adapting faster than ever. And that leaves us with a really critical question, not just for medicine, but for the future of our species. As bacteria continue to evolve their defenses, how are we going to evolve our attack?